Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good morning. So, thank you for joining the class. For those who are here, we will continue our dynamics class today. So let's look at what we are going to learn in this subtopic. So basically, we are currently under planar kinetics. If you recall, in the first class, I have informed that there are two main branches of rigid body dynamics that we are going to learn. One is kinematics, we have covered in chapter 1. And then we are now in planar kinetics, where we talk about forces that cause the motion. And in chapter 2, we have covered force and acceleration, which is basically the Newton second law of motion, F equals to ma for linear motion, and also mg is equal to ig alpha for the rotational motion. And we are now currently in the first part of chapter 3, which is work and energy, and then we are going into the second part, which is impulse and momentum. So in the previous class, we have covered the kinetic energy, and we have 3 more subtopics. Today we will go into the work or work done, and in the coming weeks we are going to discuss about the principle of work and energy, where we will combine the equation of kinetic energy as well as the work done into the principle of work and energy, and finally we are going into the conservation of energy. Okay, so let's recall what we did in kinetic energy on Monday. So basically, kinetic energy is the energy an object has because of its motion. So everything that is moving will have kinetic energy. So we also talk about the formula. Some of you are familiar with the formula you learn in physics, that the kinetic energy T is given by 1/2 mv square. And this is only the translational component or the linear motion of kinetic energy formula. So we also have a rotational component, which is given by this formula 1/2 ig omega square. So then the general formula will be combining these two. So kinetic energy T is basically 1/2 mv square plus 1/2 ig omega square. And we have 3 types of motion that we have learned previously since the beginning of this class. If the object move only in translation, then the kinetic energy will be 1/2 mv square, because omega is equal to 0. The second type of motion, when we have a rotation about a fixed axis like this, you can imagine that this blue color is whatever object it is. It can be a rod, it can be a disc. So there is a fixed point O, and this whole thing is rotating about point O. Then the formula to calculate kinetic energy will be both, which is 1/2 mv square plus 1/2 ig omega square. Or we can also calculate about point O rather than calculating the mass moment of inertia about point G. We calculate about point O, then we can simplify this equation into 1/2 IO omega square. So you need to find IO by using the parallel axis theorem. And the last type of motion, where we have general plane motion, also this will involve both formula, which is translation component and also rotation component. And if we are able to locate the location of IC, most of the time when it comes to general plane motion, this involves a rolling object, a wheel rolling on the ground. And if it says rolling without slipping, it means that the contact point between the wheel and the ground is the location of IC. So that is a clue there lah. So you can also use both component of kinetic energy formula, or you can use the other formula, which is 1 over 2 IIC omega square. And to find IIC is the same like finding IO, where you need to use the parallel axis theorem. Okay, so we did several example for kinetic energy, and today we are going into a new subtopic, which is work done. Okay, so have you heard of work done before? I think most of you have learned in physics work done. So let's revisit what is the definition of work done. So if you read here, a force F will do work on an object only when the object or the body undergoes displacement in the same direction of the force. So let's say we have a box here lah. So when we draw the free body diagram of this box, we're going to have the weight pointing down, mg. We're going to have the normal force because the box is in contact with the ground. And let's say we have a force F that is currently pushing the box. So what's going to happen to this box? The box will then travel or slide, translate linearly to the right. Okay. So now the question is, which forces are doing work in this case? You can see that after we draw the free body diagram, we have three external forces acting on this box. So based on the definition of work done, a force will do work only when the object undergoes displacement in the same direction as the force. So all of these three forces, which one do you think has the same direction as the displacement, as the motion of the object? Which force is in the same direction as the motion? Anyone? Is it mg? Is it na? Or is it the force F?
Force.
The force F, yes. Because the object is moving to the right, or basically is moving in x-axis, horizontal. And we have two forces in y-axis, which is mg and also na, reaction force. But only force F is basically acting in x-axis, in horizontal axis. So in this case, what we need to know is how far the object has traveled, which is delta S, which is the displacement lah, how far the object has traveled. And when we know the distance the object has traveled, then we can calculate the work done by the force, which is simply multiplying the force itself dengan the distance. So if you have 100 Newton force pushing the box, and the box has traveled, let's say, 5 meter, then the work done by the force F will be equal to 100 times 5 meter, which will be equal to 500. And what is the unit for work done? It is the same unit as the kinetic energy, as the energy, which is joule. So you have the what do you call, the force itself, which is the unit of force is Newton, multiplied with the distance travel, which is in meter, and you will get the work done with a unit of joule. So basically Newton meter. Newton times meter will be equal to joule. Okay, so that is work done of a constant force. So let's take an example of a force acting at an angle like this. So what do you do when the force acting like this? What we need to do is we need to resolve this force into x and y component. So when we do that, we're gonna have fx acting in the horizontal direction. We're gonna have fy acting downwards in y direction. So in this case, the object, when the force is applied at an angle like this, the object will still move to the right. So in this case, which force is doing work? Now we have mg and a, and the force F has been resolved. So we have Fx and Fy. So we have four forces acting on this box right now. So which one is doing work based on the definition of work done? Anyone? Which one is doing work, do you think? Is yes, is Fy doing work? No, because Fy is also acting in y-axis. So in this case, the work done by force F is only multiplying the force in x-axis Fx multiplied with the distance lah, delta S. The distance remain whatever distance it is, 2 meter, 1 meter, 5 meter, but you do not have to multiply the actual the force F itself, the original force, but you need to take the one that is in the direction of motion, which is Fx lah. So Fy kita perlu ignore. We do not have to calculate Fy in calculation of work done. So this, be extra careful about this. Some of you, some of the previous student, just simply take F, the force F multiply with delta S, which is wrong, because when the force is acting at an angle, you need to resolve and only take the force that is in the same direction of motion to multiply with the distance. Okay, so that is work done of force, of a constant force. Now let's say that we have a box now that is traveling from top to bottom like this. So this box here, if you release the box from a certain height, and it will go down like this, it will go down. The only force that is acting on the box when you release it from top is only the weight, which is mg. So in this case, you can see the direction of motion of the box is no longer in x-axis, but now it is in y-axis. So now the weight itself is doing work because the weight is in the same direction as the direction of motion. So now what we need to do is we need to know what is the distance, the height that the object has fall down. So the height is called delta y. Dia sama je. Previously we call it delta S because it is the displacement. Now we call it delta y because it is the height that the box has traveled from top to bottom. Or it can be the other way around lah. Box can also travel from bottom to top if some force is given to it. So in this case, the formula to calculate the work of weight, we use the symbol U. I forgot to mention previously. For kinetic energy, we use the symbol T in dynamics to indicate kinetic energy. But for work done, we use the symbol U. So previously for work done by the force, we use the symbol UF because the force is labeled as F. If let's say the force is labeled as P, for example, then you use UP lah, whatever the name of the force lah. If the force is force B, contohnya, then you write it as UB, just to indicate the name of the force. So in the case of weight, we know the height that the weight, the box has traveled down. We call it delta Y. And you will calculate the work of weight by using UW to indicate the work of weight. The formula is minus W times delta Y. So W here is basically mg lah, but it has a negative sign in front. Okay, why? Because it is traveling down lah in the negative direction of y-axis. So this is the formula, minus W times delta Y. And if you see, if the body moves downwards, if the object is moving down, which means that delta Y is also negative because it starts from top moving to bottom. So if the top, the y-axis is positive upwards, then a downward motion, delta Y punya value will be negative lah. So in this case, when delta y punya value is negative, you have a negative sign in front, then it will cancel out, and therefore the value of UW will be positive in the case of body moving downwards. Why? Because delta y is negative. If the body is moving upwards, so meaning from bottom naik ke atas, from bottom to top. So in this case, delta y punya value will be positive because delta y starts from bottom going up in the same direction as positive axis, positive y axis. So in that case, when delta y is positive, then the whole thing will be negative sebab in front there is a negative sign. So what you need to understand here is that when the body moves downward, which is in the same direction as gravity, then you're going to have UW of positive. When the body move upwards against the gravity, then UW will be negative. Okay, so now we have learned two types of work done. One is work done by the force. Second one is the work done by weight. So now some problems also involve spring. So we also have work done by spring force. So this is a spring that is unstretched. If you take a spring, original condition of the spring, nobody is pushing it, nobody is stretching it, then you have a unstretched length of the spring. We call it, this is the original length of the spring, panjang asal spring tersebut. So in this case, when the spring is unstretched or not compressed, then we have the spring force Fs equal to 0. When we compress the spring, then we're going to have some compression length. So daripada original length, let's say original length is 1 meter. 1 meter is too long. Let's say the spring is 20 centimeter lah, 20 centimeter spring. Then you compress it. You compress until the spring has become 15 centimeters. So the compression length is actually 5 centimeter, not this part of the length. It is the compression length. So we call this as S. It can be S1, S1 lah, normally S1. So when the spring is compressed, then the force developed in the spring force is given as minus K times S1. K is the spring constant. I think you have heard of this before. Every spring has its spring constant that indicates the strength of the spring lah. If the spring constant is very high, then the spring is very hard to be compressed or to be stretched. Kalau K too small, then it is a very very not so strong punya spring lah. So this is the spring in compression. To calculate the spring force is to multiply minus K, the spring constant, with the compression punya length. Same goes for stretch. If you stretch the spring, then to calculate the spring force is to multiply negative K, negative spring constant, with the stretch punya distance, stretch punya length. So the work done then by the spring is given by US, which is the formula is negative 1/2 times K. K is the spring constant, multiply with S2 square minus S1 square. S2 is the compression or the stretch of the spring after the spring has been stretched. S1 is the initial condition. Later when we do the tutorial example problem, then you will see how do we get the value of S2 and S1. Now I just want to introduce to you that this is the formula to calculate the work of a spring. Okay. One thing that many students have made mistake before is that they take the length of the spring when it is compressed as S1. That is not S1. And also sometimes This is called the compression punya length. Bila kita compress, spring that has been compressed tu berapa panjang dia. That is not S1. S1 is taken from the unstretched length ni. This one is S1. This is the length of the spring original. So basically S1 is the original length. You have to minus the compression punya length. Then you get S1 because S1 is the one that is on this side. Same goes for the stretch punya situation. When the spring has been stretched, then the S2 is not this length of the spring, but S2 is basically the stretch punya length. You have to minus with the original length of the spring. So please be careful about this lah. Later in the example nanti we can see how we get the S1 and S2 value. Okay, so this is the work done by spring force. Now, so when we summarize, there are a few types of work done. One is the work done by a force, which you multiply the force with the distance. Then we have the work of a weight, where you multiply negative of the weight with the distance it goes down or up, delta y. Delta y will be negative if the object travels from top to bottom. Delta y will be positive if the object travels from bottom to top. So that will you have to be extra careful. We also have the work of a spring, which is the spring could have several conditions, either it is compressed or it is stretched. And then the last one, we also have the work of moment, of a couple moments. So let's say a moment is acting on an object and cause the object to rotate. Then if you imagine a rod lah, for example, a rod. So let's say the rod is 90 degrees and there is a moment of 100 Newton meter acting on the rod, which makes the rod turn to, the rod is horizontal, and because of the moment, the rod is now rotate until it becomes vertical. So the rotation angle is basically 90 degrees. So in this case, when you want to calculate the work done by the moment, is you multiply the moment, which for example, the moment is 100 Newton meter, multiplied with the angle, how many degrees the object has rotated. Let's say 90 degrees, but the angle has to be in radian. So you need to convert 90 degrees into radian. So these are basically 4 types of work done that you will have to calculate when you solve the problem related to this lah. Okay. So let's, do you have any questions so far before we move into some of the tutorial or some of the example calculation? Any question on the work done? Okay, I assume that there is no question. Let's move to the first example. So a 50 kg wheel is subjected to a force of 50 Newton. So you can see the force P is applied at an angle and will cause the wheel to move to the right lah. If the wheel starts from rest with and rolls without slipping, determine its angular velocity. So this question is for the next subtopic. We are not there yet, but now what we want to do is you just ignore what is written at the back here. What we want to calculate is after 10 revolutions, after the wheel has rotated 10 revolutions, meaning that the wheel rotate satu pusingan, dua pusingan, tiga pusingan, you can imagine it move. After 10 revolution, what is the total work done of this wheel? So that is what we want to calculate. Now we just focus on the work done. We are not calculating the angular velocity yet. Okay, so to solve this type of problem, first you need to draw the free body diagram. So we learn about free body diagram in chapter 2. So basically this wheel will have a weight here pointing down. It has a contact between the ground, between the wheel and the ground. So there is a reaction force or normal force NA at the bottom, and the force P is acting at an angle of 30 degrees. So basically we need to resolve into components. So we have X component P cos 30 and we have Y component P sin 30. This is the initial punya position. So after 10 revolutions, the object will move to the right. So what we want to know is the distance. So we need to find the distance here. Okay. So before we go into the distance, after we look at this free body diagram, we know that the object is traveling in horizontal direction. So all forces that is acting in vertical direction will have no work done. So basically the mg has no work done, normal force no work done, and P sin 30 no work done. The only force that has work done in this case is only P cos 30. So we now know to calculate the work done is P cos 30 times the total distance. So we need to know the total distance lah. It moved from here, position number 1, going to position number 2. We need to know what is the distance. How do you get the distance from here? Anyone has an idea? How do you get the distance? In the question, it says the wheel travel or rotated 10 revolution. This is the clue. How do you get the distance from 10 revolution? This is our clue here, rotated 10 revolution. So basically what we want is what is the distance from here, from center of the first position to the second position. So this is basically our delta S. Okay. So how do you get the distance? Anyone has an idea? Anyone has an idea? How do you get the distance from 10 revolution? What does it mean? One revolution. How far is one revolution? When you take a wheel, the wheel has rotated one complete circle, one complete revolution. So one revolution, how far is it?
IR.
Sorry? IR apa?
2 pi R.
2 pi R. What is 2 pi R?
1 revolution.
1 revolution. Apa 2 pi R tu calculate apa? 2 pi R is the formula to calculate the circumference, ukur lilit. Ukur lilit apa ni, satu circle lah, satu bulatan. So, one revolution means if you look here, if I zoom in here. Oh, sorry, saya tak boleh ni. Okay. Where is my pen? Okay, one revolution is the wheel circumference, which is given by 2 pi R. So I want to write here. Okay, so one revolution means if you start here, dia akan pusing satu revolution ni sampai bawah, sampai sini balik. That is one revolution. So basically, what we are trying to calculate is the ukur lilit, is the circumference of the wheel for one revolution, which is given by 2 pi R. So, and then 2 times R. R is given by 0.4 here. This is the value of R, 0.4. So 2 times 0.4 is 0.8 pi. So that is one revolution. Now we are talking about 10 revolutions. So it's basically 10 times of the ukur lilit, of the circumference of the wheel. So for 10 revolutions, we will have 8 pi as the distance lah, 8 pi. So when you times 8 times pi of 3.62 and so on, you will get the distance in meter lah. So now basically what we do is to calculate the work done by force UF is 50 cos 30. Remember, now P is to be multiplied with cos 30. We do not take 50 Newton sebab kita dah resolve into components. So 50 cos 30 times 8 pi, then you get the answer of 10 or 1088 joule as the total work done for the wheel to move from position 1 to position number 2. Okay, any question on the first example? So it is very important that you know how to draw the free body diagram correctly, because from the free body diagram, you can identify which force is doing work and which one that is not doing work. Okay, so let's move on to the next example. It is still a rotating punya problem. Previously, this is a general plane motion problem lah, because this thing is not only rotating, but it is also moving to the right. So this is a general plane motion problem. Now we move to the rotation about a fixed axis punya problem. So let's read the question. If a uniform 30 kg slender rod starts from rest, determine angular velocity. Doesn't matter. We do not want to calculate angular velocity yet. What we want is the total work done. So you change a bit this question. Determine the total work done after it has rotated 4 revolution. Okay, ini pun sama. Same concept as the previous question. And one important information also here is that the forces remain perpendicular. So this is important to understand. The forces remain perpendicular. Okay, so let's first draw the free body diagram of this rod. So when you have a rod like this, we have basically 4 forces acting on it. One is the weight mg pointing down. This is the center of gravity lah at point G. And we have force P1, 30 Newton. We have force P2, which is 20 Newton, and we have the moment, which is M, that is equal to 20 Newton meter, acting on this thing. So because of the moment, the rod is rotating lah. Okay, so we know that it has rotated 4 revolution, meaning that 1 revolution is 360 degrees. Now we are not talking about the circumference tadi, because this is clearly not a circle, not a wheel lah. So now for 1 revolution, it is 2 pi. 2 pi here means 360 degrees lah. This is 360 degrees. Okay, 2 pi is 360 degrees. Converted into radian, it becomes 2 pi. So for 4 revolution, you multiply 4 times 2 pi, which will give you 8 pi radian. So basically, we have the delta theta. Delta theta is basically how much the angle or the rotation of the object ni berapa radian lah, which means it is rotated 8 pi radian. So from here, we can calculate the work done by the moment, UM. Because previously I have shown the formula to calculate work done by moment is to multiply the moment with the total angle that it has rotated, but the angle has to be in radian. So that's why we calculate this in radian. So we have 20 Newton meter moment. So basically 20, moment is 20 multiplied with 8 pi, because it has rotated 4 times. One rotation or 1 revolution is 2 pi. So 4 revolution will be 8 pi. So you get 502.65 joule for the work done by the moment. Okay. Next, do we have work done by the weight mg here? Anyone can tell me whether mg is doing work or not? Do you think that mg is doing work, or do you think it is not doing any work? Okay. To understand whether the weight is doing work or not, let's imagine that I'm not sure if you can see this pen here. So let's say that this is the initial position. So the thing is rotating 4 times. So this is 1 revolution, 2 revolution, and so on. And after 4 revolution, it comes back to this position again, which means that although mg is traveling in a is traveling during the motion, mg is going down and up and down and up. But in the end, after it has completed 4 revolution, the mg or point G is back at its initial position, which means that there is no delta Y. So in this case, no work done by the weight because delta Y is basically equals to 0 because point G starts here. After 4 revolution, it comes back to its original position. Unless question dia kata, dia start from here and then rotate to here, 30 degrees or 60 degrees, for example. Now you can see there is a change of position of point G. Point G is here. So in this case, in the case of this question, mg or weight is not doing any work because after completing 4 revolution, dia balik ke kedudukan yang asal. Okay, so let's talk about the force P1 and P2. So during the rotation, P1 will travel around this circle and P2 will travel around this big circle. So when it says the force remain perpendicular, it means that during the motion, the force P1 to follow the apa ni the rod punya direction lah, the rod punya angle like this. So at this, when the rod is in this position, P1 is pointing this way, P2 is pointing this way, and so on. Therefore, P1 and P2 tu the direction dia adalah we have to multiply dengan this circumference. Dia sama macam yang soalan wheel tadi. So basically UP1 is equal to P1 multiply with delta S1. So delta S1 is basically 4 times of this circumference of the small circle here. Okay, so basically how do you get this small circle is by using this formula. S equals to R theta. S1 is equal to R1 times theta. So we know R1 here is 0.5 meter lah. This is R1. Okay, this is basically the radius of this small circle lah. This is R1 over here. Okay, so we got 0.5 multiply with the data we know, we have calculated previously that the object is traveling 8 pi. After it has completed 4 revolution, it is 8 pi. So then we have 4 pi here. So UP1 is basically 30 Newton, which is the force of P1 here, multiply with 4 pi, so you get 377 joule. This is the work done by the force P1, which is 30 Newton. Now move on to the force P2, which is 20 Newton. You do the same. UP2 is equal to P2 times delta S2, which now delta S2 is the big circle. So to calculate delta S2, we use the same formula. S equals to R times theta. So R now is 1.5. Okay, R now is this 1.5 is now R2, which is the distance from force 20 Newton to the center of rotation, to the fixed point O. So this is R2. Therefore, you got 1.5 here, multiply with the total angle that it has rotated. We calculated before, 8 pi. So you get 12 pi here. And UP2 is then 20 Newton times 12 pi. You get 754 joule. So now we have 3 work done in the motion of this object. So then we can calculate total work done by summing, by adding up all this work done. 502.65 plus 377 plus 754, we get the total work done of 1,633 joule. So this is how you calculate the total work done. Okay, any question on the second example? Okay, so if there's no question, let's move on to probably the last example for today. Next week, we are going into the principle of work and energy, where we will calculate the angular velocity next week. And the class next week will be as usual, face to face. Okay, so let's read this question. This is again another general plane motion problem where the object now rolls on the ground. 20 kg wheel has radius of gyration, okay, because this is non-homogeneous, so radius of gyration is given. When it is subjected to a couple moment, 50 Newton meter, okay, so there is a couple moment acting on the wheel. It rolls without slipping. Now, we do not want to determine angular velocity, but we want to determine the total work done first after it has traveled 20 meter. So now, the travel distance 20 meter is given. Okay, so let's draw the free body diagram of this wheel. So basically, we have the weight pointing down, the normal force pointing up, and we have a moment. These are the only forces acting on the wheel. So by looking at this force here, three forces, which one is doing work? Or let's look at the motion. This is position number 1. This is position number 2. So basically, due to the rotation of the wheel is traveling from position 1 to position 2, left to right in the horizontal punya position lah, horizontal motion. So which one is doing work? This out of these three forces. So clearly, mg and na is not doing any work because mg and na is acting in the vertical axis, in the y-axis. The one that is doing work is only the moment, because the moment is acting acting a rotation punya force, which cause the wheel to roll to the right. Okay. Now we know the distance 20 meter, but the question, the formula to calculate the work done by moment, um, is to multiply the moment with the total angle. So now we do not have the angle, but we have the distance travel. So we need to calculate the angle delta theta that the object has traveled. So if we have the distance 20 meter, how do we get the angle? So we can also use the same formula like we used before, which is S equals to R times theta. R being the apa ni, radius lah. This is 0.4 is basically the R, the radius. What we want is this theta here. So we know the S, which is 20. 20 meter is the distance that the object has traveled. So now we want to know what is theta. So using this formula, S equals to R theta, R is 0.4, we get the value of theta 50 radian. So this formula will straight away give you the value of theta in radian, not in degrees. So you do not have to convert again to degrees lah. What you get here, 50, is already in radian. So once we have the theta in 50 radian, we can then straight away multiply the moment, which is 50 Newton meter, with 50 radian to get the work done by moment, equals to 2,500 joule. Okay. So any question so far about calculating the work done? So basically, if we recall the work done previously, there are 4 types of work done. So we have calculated, I have shown the calculation of work done by force, and I have also shown the work done by moment. In the next class, we will look at the calculation of work done by weight and also spring, and we will go into another subtopic, which is the principle of work and energy. So if there is no question, I think that will be all for today, that we have covered work done. When we go into the next subtopic, the principle of work and energy, that will also involve a lot of work done calculation. We will calculate the work done as well as the kinetic energy, and we will combine both into the principle of work and energy to find the angular velocity. Okay, if there's no question, I think that's all for today. Thank you for joining the class. As usual, I will share the recorded session today, and also the slide. Also, I have updated the column with the videos, and also the notes on the kinetic energy as well as work done. Okay, so if there's no question, thank you everyone. I will see you again next week, Monday, face to face, 8:30 a.m. at DPM. So the class today will end here. Thank you. Assalamualaikum and have a good day.